Well, we have 17 minutes.
Can you explain SMPC in 17 minutes?
Let's give it a shot.
So what is SMPC? What is this thing that we're adding or we're doing?
SMPC, in short, allows you to split a secret into two values that are stored in two different locations that can together do a computation over it, in which no one learns any of the values until the final result, where they come together and reveal the result.
Right. And I'm guessing this is more complicated than just like taking half of the bytes and putting them in one place and taking the other half and putting them somewhere else.
Yes, but not a lot. It's a little bit more complicated. If you were just splitting the data up in two halves, then each party would still learn half of the bytes. And we don't want them. We want them to be able to learn absolutely nothing with the information that they have. So instead of splitting the bytes in half, what you do is you take each value and you generate two random values, but not just two arbitrary values. You generate two random values such that if you add them together, they become the value you're trying to store in there.
So we have this iris code, which ends up being one very big random number. And what we want to do is to find two numbers that when added together, they turn into the iris code.
Almost. The iris code has 12,800 bits in it. And we take each individual bit. We encode those bits in 0, 1. Actually, -1, 0, 1. We'll get into that later. But we encode each bit into 0, 1 in a 16-bit integer. Then we create two random 16-bit integers such that when you add them together, they are either 0 or 1.
So for each single bit, we convert that to a number, and then we generate two random numbers.
Yes.
So that when adding those numbers together, it becomes either 0 or 1, representing the encoded value of the bit. Then we have a big array of numbers.
That is correct. So instead of having 12,800 bits, we now have 12,800 16-bit unsigned integers.
Wait, but we have a pair of numbers, right?
Two, we have that times two, one for each of the two participants in the system.
And we give this to each participant.
Yes.
Can this be done for more than two participants, or is it exclusive to two?
This scheme actually works for as many participants as we want here. However, a future iteration will be a little bit more complicated and have different requirements. That one actually specifically requires 3 participants.
So we have this array, and I'm guessing just like give the array, like one of the arrays to each participant, and that's about it.
Correct. Like you take an iris code, you generate these two arrays of random numbers, and ship one to one party, ship the other to the other party, and that is how the iris codes can be stored securely in an SMPC setup.
Okay, so how does this then allow us to do computation over it? Because if I just like split it in half, I wouldn't necessarily be able to do computation over them and just like having value
Yes,
values.
that is correct. And this is where the magic starts. So maybe this is a good point where we can use the whiteboard. So you have your secret value, which is stored.
That secret would be a number, like an integer.
Yeah, in fact, this would be a 0 or a 1.
Okay.
Then we store this as two values, a plus b. And these can be anything from 0 to 2 to the power 16 minus 1.
And this would be the values that like the parties have?
Yes. And these are random. Independently, these are uniformly random. So they reveal absolutely no information. It is only when you add them together, modulo 2 to the power 16, that you get the original result back.
Yeah.
So this is how a very simple so-called additive secret sharing scheme works. Now, the cool thing about this is what you want to do when you're computing an iris code distance is compute a Hamming distance. So an iris code is basically a large vector of bits, and you will have two of them that you need to compare. And what you want to know is the Hamming distance, which is how many of these bits are different. This will be a value from 1 till n, the length of the bits, which is 12,800. So the way you would normally do it is you would sort the two together, and then you would do a pop count over it. So basically sort them together and then count how many ones you have, because those will be the bits that were different. Now we're working in a different thing. Now we're working actually in it's very mathematical, but it's actually really easy, the ring of integers modulo 2 to the power 16. What it means is you basically have access to all your standard algebra, except division doesn't always work.
Okay.
So it's a lot of fancy words for saying that math works the way you think it should. So first of all, let's arithmetize this operation. So this is bit operations, pop counts and XORs and all those things. They're not super useful in cryptography because they're not algebraic. But we can rephrase this as an algebraic operation. So actually, this is where I think I'm going to shift to the -1, 0, 1. So instead of encoding bits as 0, 1, let's do it as -1, 1. And now if I have -1 on one side times -1 on the other side, I get 1. If it's 1 times -1, I get -1. Same if it's different in the other way. And if they're both 1, the end result is also 1. So what you're now seeing is that if the two are the same, the result is 1. If the two are different, the result is -1.
So what you're doing is basically building a rudimentary XOR operation by just...
Exactly, yes. So what we've done here is we took the XOR and it now sort of turns into multiplication. The other thing is pop count. You can kind of see where this is going. Instead of counting, the pop count is already basically a sum, right? You just sum the zeros and ones together. So that's what we'll be doing here as well. It's a little bit different because we're not summing zeros and ones, but you can correct that with a simple formula. So now we've arithmetized this thing where we had 2 iris codes before. Instead of computing the Hamming distance as, let's have iris code P, or iris code Q, and then we pop count the whole thing. Instead of doing that, we can now do something like arithmetic, like sum over all these -1, 1 values, Pi times Qi. Sounds fancy, it's just the sum of a product. Specifically, you may recognize this thing from linear algebra. This is a dot product. This is basically the same thing as the dot product of the vector V with Q.
Which doesn't make it any simpler to solve because it's very simple. It's just like more notation for the same thing.
It is, but this made us realize that we can actually use some of the recent advances in SMPC that have been used in machine learning. Because machine learning uses a lot of matrix multiplications. Matrix multiplications are basically fancy dot products. So all of that recent work that happened in the last couple of years in SMPC for machine learning can also be used to do any kind of dot product, specifically this dot product here. So now that we've gone through the steps to turn the problem we're trying to do and turn it into a dot product, now we can use the tricks from secure multi-party computation and actually solve it this way. So let's say that instead of Pi and Qi, P turns into, let's call it AI plus P.
Okay, so you have 2 parties. Each party computes the Hamming distance for each bit and just like, I guess, gives their value to like a shared pool.
So the 2 parties each hold one of these shares. So this is party, let's call party A, and let's call this party B. For all the iris codes that they have, let's say this is iris code 0, iris code 1, up until iris code, like however many there are in the set right now. So party A will have all the A vectors. Party B will have all the B vectors.
But in order to get the full distance, you still need to like put them together, no?
Yes. So when a new iris code gets added, we turn this also into -1, 1 encoded vector. And let's call this Q for query. This is getting turned into just one vector that is shared with both. So it's not secret shared in this sense. This is just a direct encoding. But what this allows you to do is party A can now compute sum over Qi times P n AI for each n. So for each pre-existing iris code. Party B does the same thing. Again, it computes a sum over products, but now over all the B shares. These results, the outcomes here, let's call them distances because these are Hamming distances. So this will be distance n share A, and this will be distance n.
These are the distances between the iris code I want to check if it's similar.
Yes.
which is not encrypted, and each share.
Yeah, this is the iris code you want to check if it's unique, if this user hasn't tried to sign up before. So what you'll do is you need to compare it against the previous iris codes to make sure.
And it holds that like you can get the distance by checking against each of the shares without needing to combine the result to get the distance.
So this is not the distance yet, but what I'll claim is that the actual distance to the end iris code is simply the shares added. So what happens is we have a coordinator that talks to both of these parties. It submits the query to both parties, and then it gets these distance results back. Now these distance results are just one 16-bit number per comparison, so they don't reveal the entire vector or the entire share. In the process of doing a single comparison, the coordinator doesn't learn the secret shares, it just learns a share of the secret distance. And it adds those two together, and then it gets the plain text distance, and it can match it against the threshold and know whether it was a match or not. And then to show you how this works, you can write this out. So this will end up being this sum qi times p and ai plus the sum over qi times p and ai. Then you can group like terms, and you'll get sum over I of qi times p and ai.
But you extract the factor from the sum, meaning that you can just like multiply individually.
Yes, these are, I mean, this is just algebra, right? You're taking the sum with the same indices, so you can group the sum together. Now you're summing over qi times something plus qi times something, so you can take these qi out. But the important thing is that this thing is our secret share. So here...
So that meaning that that is equal to...
E and I, the thing we originally wanted to compute.
That is great. That is really convenient. I think that's it. That is honestly a lot simpler than I expected.
Right?